Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everyone. Good morning. Welcome to the talk. So today, we're very pleased to have Professor Hayati Gunawi from University of Chicago. He will be visiting Microsoft for a week. And for all of you coming to today's talk, you buy one, get one free. Because in addition to today's one, Professor will give another talk in tomorrow morning on very similar topic but a different content. So the talk will be given in Building 43, where the Azure teams are. So you're welcome to join in person or watch from online. So Professor Gunawi has been doing very impactful research in the area of distributed systems, focusing on scalability, performance, and reliability, all of which are at the heart of all of us as a cloud-first company care most about. So we're very interested in what he's been working, and I try to explore collaboration with him. Okay, without further ado, I'll take it.
All right, okay. Thank you, Chung, and thank you for having me. So yeah, I'm Haryadi Gunawi. I've been an assistant professor about 4 years at the University of Chicago. So back there, I lead the UCARE lab, which stands for U of C System Research on availability, reliability, and efficiency. I thought the name is cute and kind of unique, but in 2012, I was curious. I searched the word UCARE U Chicago, and I was surprised that my group page is way like down there. And I realized that there's another UCARE on campus that stands for U Chicago Alcohol Risk Reduction Education, drinking problem. But in 2014, I do the search again. So right now I'm like number 2, which is okay. I think alcohol risk reduction is more important than cloud computing, right? Okay, all right. So let's go back to this question: what new bugs live in the cloud? The word cloud is such a buzzword in this talk. Cloud means data center distributed systems. So initially, I didn't have the answers to these big questions. I just deal with one laptop basically every day, right? But if we look at the bug repositories of modern cloud systems, it's just amazing how many bug reports that have been submitted, right? Literally like tens of thousands of them. So back in 2014, we kind of studied about 3,000 issues, tried to kind of find interesting bugs. So I think we were successful. I think we came up with several interesting new classes of bugs that are specific to cloud scale distributed systems. The first one is the problem of what we call as distributed concurrency bugs, where messages and events can arrive out of order, not just messages, but including failures that can also arrive at different timings. And then we also found the problem of non-deterministic performance bugs, meaning that sometimes our jobs run fast, but sometimes our jobs are stuck in limping mode and cannot get away from it. We also found an interesting problem of scalability bugs. You scale out your systems, but the bug symptom might not appear in small or medium scale deployment. But when you start deploying more than 100 nodes, 200 nodes, suddenly you see the bug. Okay, that's what we call as scalability bugs. And then there are other outage causing bugs. The first one is what I call single point of failure or cascading bugs. Basically, if you hit this bug will happen in every machine in your system, such that all the machines will die and you get an outage. And then I also see lots of cross-layer upgrade bugs where you upgrade one layer, everything is fine, you're happy. But turns out that upgrade in one layer causes problems in many other layers in the whole ecosystems. And I'll talk this other stuff tomorrow. But in this talk, I'll focus in the first 3 stuff here, which is what my group has been dealing in the last 4 years. Okay? Right, so let me begin with distributed concurrency bugs, or DC bug for short. So what is a DC bug? A DC bug formally is caused by non-deterministic timing of concurrent events involving more than one node. And most importantly, when we say events, this is not just messages, but it's also include crashes, reboots, timeouts, and maybe some local computations from background jobs. Okay? And among all the bugs that we study, we find that 6% of the bugs are about DC bug. So this is quite very common in the bug reports. And they get, they can give severe implications, data loss, downtimes, inconsistent replicas, hanging jobs, and so on. Yes?
What is your data set when you say
oh yeah, so I talk more about this methodology tomorrow, but we review about 20,000. We take 3,000 that we feel really affect the development and deployment issues. Okay, so among that 3,000 within a 3-year window, from the bug repositories of those systems that I show in the table in the beginning. It's called Jira. So Hadoop Jira, Cassandra Jira, outpaced Jira, tens of thousands of them public. Yep. Okay.
So for all those bugs, do people have a way of assess the severity of these bugs? Like some of them, I guess they will fit into one of these, right? But then in terms of the end effect, some of them are more severe than other.
I would say the ones that we include, those 3,000, it's labeled major or critical, right? So these really 6% are really critical ones, because when you have this, you could corrupt the system state. Yep. Mm-hmm. But there are many others that we ignore, like adding one parameter to function and so on. Okay. Yep. So okay. So this is a simple view of a DC bug. We have 3 nodes. Time goes down. We have a message BC comes early before a message AC, and if this is the case, then everything is fine. But it is possible that the message AC comes a little bit early before the message BC, and when this happens, node C gets confused and gets an error. Okay, so just a simple view of messages that arrive out of order. Now this is a real view. This is a Paxos bug in Cassandra. So we have 4 nodes here. Time goes to the right, and we have 3 concurrent updates from the client. We denote this with red, blue, and green. What you see here, we have 3 message races. That is a message that goes out of order. We have this red one, N, coming after N, M, and then we have the blue one, P, arriving after O, and then we have something R after Q, and then if you have these combinations, you're going to get to the bug and you get a data loss. Okay, so this is a real view what is happening. It took 24 hours to understand, so my student Hannah Korn back there was the one who studied this bug, not me. Okay, so again, this is the idea of messages coming out of order. But in addition to messages, we also need to think about crashes and reboots. Let's take this example, bug example, Zookeeper. So up here we have 3 nodes. They elect a new leader, B becomes a new leader, but then B crashes, C becomes new leader, and then C receives a new transaction from a client, but before fully committing, A crashes, C loses quorum, C crashes, A and B back online, and so on, okay? And I even cannot follow myself here. But the point is that at the end, we have permanent inconsistent replica, where some nodes believe transaction 11 is Y, and the other one says transaction 11 is X, and cannot be reconciled. Okay? What is the takeaway point? Again, we have deep inside here, we have messages that arrive out of order. But in addition to that, we also have crashes that must happen at specific point in time here to get to the bug. And not only one, we also need to inject multiple of them. Now, after you crash, you need to decide whether you want to reboot the node. And again, you need to inject reboots, but then you need to reboot at specific timing to get to the bug. Okay? So all of this could happen in any order, and in one specific order, you're going to get to the bug. Okay? So this is what I call like deep, really deep concurrency bugs, right? So how can we catch deep concurrency bugs? Well, the state of the art in the last 5 years, people have been using what we call as distributed system model checker. So just imagine, let's say you have a distributed systems with 2 nodes. Don't worry about the details here. And then these nodes communicate with each other. For example, you have A, B, C, D as outstanding messages. What DMCK would do is it will intercept all these messages, and rather than letting them go through, this interception layer will tell the DMCK server that these are the outstanding messages. And then the DMCK server decides, okay, how about at this point we enable C? So C will go through and will be processed. So with this, this will run very long time. Basically what you've done is that you've exercised many non-deterministic orders. You try ABCD, ABDC, ACBD, and so on. And at the end, with the hope that you will find the buggy paths, the buggy interleavings. Okay? So that's what DMCK. Now again, just an illustration here. You try different orders. Maybe everything is good, but at a specific order, you're going to hit the bug. And then, yeah, you go that, you repeat that 10 times to understand what's going on and try to fix the bug. Okay. All right, so that's basically the background of DC bug. So now let me introduce our work, SAMC, semantic-aware model checking, and why we introduce this method. So we kind of ask, okay, what's wrong with existing model checkers? I mean, in the last 7 years, again, there are lots of model checkers that have been proposed, including some from Microsoft Research as well. But again, if we look at this illustration, this is a simple illustration, but behind it, there are about 100 events that we need to permute. So lots of events to permute, but in addition to that, again, we need to add crashes and reboots. So at the end of the day, we're going to get a really big state space explosion. Okay? And in fact, if I look at all this research, I found that most of these checkers skip injecting multiple failures, not even reboots. So we cannot really find deep bugs unless we do all of this. Yes?
How's the model generated?
Right, great. So there's a difference between the classical model checking term and the new term, what we call as software model checking, which means that we do not create the model. Instead, we intercept all the non-deterministic events and just reorder them like crazy, and we write some kind of specification. For example, there should be only one leader at all time. So when you reorder all these messages and you find out that there are 2 leaders at one point in time, then you say, there's a bug. Okay? So this is a kind of different the way I think system community take the approach of model checking from the PL community. Yep. Okay. Right, so I think the question is, how can we catch these deep bugs really fast? Now, if I look at existing model checkers, I find that they treat the target systems as a black box. For example, let's imagine you have one node, and there are messages coming in, A, B, C, D, and they are concurrent. If you treat it as a black box, then you need to try to permute all the orderings. You're going to try A, B, C, D, A, B, D, C, A, C, B, D, and so on. Okay? Because we do not know how the messages will be processed. What we find is that if we could open up the box and then look at some kind of semantic knowledge inside the box, we could maybe perhaps reduce the unnecessary reorderings. Okay? And I'll show you how. Okay? So that's the idea with semantic awareness here. Now, before jumping to SAMC, let me go back to briefly discuss the notion of dependency versus independency that the model checking community has been using to reduce the number of orderings. Okay? All right, so let's imagine we have a node, the state is S, and I have 2 concurrent messages, A and B. Now let's suppose, again, we have S. Let's suppose I receive A first and then B, then maybe the node will move to S prime. If I receive A and then B first and then A, then the node will move to S double prime. If this is the case, the model checking community says these messages are dependent. Okay? We cannot reorder them. We need to reorder them. But let's suppose we know that if we do AB or BA, it will lead to the same state. The term that we use, we call A and B are independent. If A and B are independent, we know that this one is unnecessary to be tested. We should just test that one. Okay? So again, independent, no need to reorder. Yes?
So when you say A and B are independent,
Yeah.
that means for all S, A and B are
Yes, for all S, as long as the transition goes to the same state, right? So what matters is whether they go to the same state or not, because what we care is the state transitions. Yep, correct. Okay, so again, the idea is that black box, we need to declare that all of them are dependent. We need to permute all of them. But I'll show you later that if we know some kind of semantic about the processing of the messages, then we can declare some of the messages to be independent with each other. Then we can reduce these unnecessary reorderings. Yes?
So what if AB and BA take you from don't never change, so they're independent, but ACB and BCA are different, take you to different.
Then what we do is that in the DMCK, we're going to take a pair at a time. So when we take one pair, we decide whether we want to reorder those two pairs. And then we're going to evaluate the next path again, right? So in your case, so when you say ACB, right? Okay? Then I'm not going to look between A and B. I'm just going to look at A and C first, and whether I should do AC or CA. And then after that, then the system enters a new state, right? And then I evaluate the next thing again. So this is one step at a time. Am I correct in accord? Roughly? Yeah.
Okay. All right.
Okay. Or do you want to, Tanakorn is the one who implements that, maybe have a, or roughly, or we can take that offline.
Oh, we can take that offline.
Okay. Yeah. But at the end it's fast. Right. Okay, so let me give you a very specific example on how we do this. Okay, let's take a look at a simple leader election protocol. This node has a belief that the belief is 3, meaning that it believes that the leader will be node number 3. At the same time, there are new votes coming in, say that node 1 should be the leader, node 2 should be the leader, node 4 should be the leader. Now, if we look at the code of this simple leader election, there is a code that looks like this. If vote less than equals to belief, ignore it, do nothing. But if the vote is larger than the belief, we'll take the vote, and the newly expected leader will be, for example, number 4. Okay? So there's this code in this leader election protocol that we want to test. Now let's suppose we know, again, this is not a black box, we know the code looks like this. And then let's say if we want to order, decide to order 1, 2, then we will know ahead of time that 1 will be discarded. It means the state stays the same. And 2 will be discarded, the state stays the same. If I do 2, 1, we know that they will be discarded also, so the state will stay the same. So if we just look at the fact that these votes will be discarded, we know ahead of time that we do not need to order these things. This is unnecessary. Okay? So at the end, we do, at least just for these 3 concurrent votes, we do 1, 2, 4, but we're going to ignore 2, 1, 4. We're going to do 4, 1, 2, but we're going to ignore 4, 2, 1. And then we're going to need to do these 2 things, because why? Because when 4 comes in, the state has changed. And we need to reevaluate the things after that again. Okay? But of course, you see this, you can say, hey, they look the same. Can we prune that also? I would say yes. I think there's a possibility to prune them also, but at this point, looking at just this pattern, we do not discard them. So there are still rooms for improvement to reduce the number of orderings. Okay. All right, so now let me take a high-level view. So the idea here is that what we want to find is the message processing semantic. That there is a relationship between an incoming message and the current local state. For example, again, this is the leader election protocol. If you see something like this, then this is what we call as a discard pattern. That sometimes there are messages that will be discarded depending on the local state. So we see that and say, oh, that's a discard pattern, so we're going to write the discard predicate. Okay? So given a message and a local state, the message will be discarded. Okay? And if the message will be discarded, and if a pair of messages will be discarded, then we know that they are independent. Okay? So there are more details that I'm skipping here in terms of how it works, but we can talk more about that offline. But the idea that the discard pattern is general. What is another pattern? We find that there are increment patterns. Imagine that we have a bunch of acknowledgement messages coming into the node. Well, if you receive an ACK message, typically it will just do ACK count plus plus, right? So meaning that if my current counter is 0 and I receive the green and then the orange and then green ACK, they will go from 0, 1, 2. If I receive green and orange, it will go from 0, 1, 2, right? So I know that this will lead me to the same state transitions, and I can ignore that. So if I ignore that, this is, again, if I see the code like this is what I call is increment pattern. We create this predicate, and we put this predicate in the dmck server. Okay, yes?
Does this pattern include cases where the node may send another message as soon as it receives the ACK and the counter increases?
When we have dmck, we call this, we need to freeze the world, right? So we enable only one message at a time, right? That's why when we enable one, and then that one maybe creates a new messages, we're going to intercept those messages as well. But then we're going to enable 2, and then again we're going to reevaluate these predicates all the time. Every time we want to enable every event, we need to reevaluate this thing. Does it make sense?
Oh, I don't want to take more time now.
Okay, yeah. Right. So again, we do not, I think what I'm saying here is not like we know the whole path and then we decide only at one point that, oh, this independent, these are dependent. Instead, every time we enable an event, state could change in the system. So every time we enable an event, we get the rest of the path, a new path, we reevaluate again and again. Okay? So something like that. Okay, so and there's other patterns. So again, the idea at a high level, we call this local message independence, that there is a notion of independency between concurrent messages coming to one node, and we could reduce the number of orderings. All right, so I've been talking only about messages, but not really about crashes. Okay, crash is going to make things worse. Okay, so let's imagine this situation. We have, let's say, imagine a leader and a followers here. There are 4 outstanding messages on the network, A, B, C, D. And at one point, let's say you decide you want to crash X. Now the question, when do you crash X? Well, if this is a black box model checker, I need to do A, B, C, D, and then inject crash. I need to do A, B, C, then inject crash, and then D. Why? Because this crash might create many more new events that will be racing with D. So roughly, again, I need to insert X at every possible point here. Okay? But I will show you later that if we know some kind of crash recovery semantic of the systems, we could reduce these unnecessary reorderings. All right, let's take a look at this example where we have, again, leader and followers. And then let's say you want to decide that you want to inject a crash on the follower. Okay? So if we look at the crash recovery semantic at the leader, usually it looks like this. If you crash the follower and the ensemble still maintains a quorum, the leader will just decrement the follower count, which means that when you crash this, there will be no new messages that the leader will create or the system will create. So when you crash a follower, you're going to just create a local impact at the leader, and there will be no new messages and only state changes in the leader. Right? So what that means is that I do not need to inject X at all these possible interleavings, because they would lead to the same state. They just decrement the follower count. Okay? However, if you decide that you want to inject a crash on the leader, and this is usually where the fun part is, okay, where all the bugs is, Then if we look at the code, it says if the crash is a leader, and again, of course, you don't have a quorum if you crash the leader. Again, this is just, what happens is that the system will elect a new leader, meaning that all the nodes will go back to the searching state and try to find a new leader. All these new red messages could be racing with these outstanding messages A, B, C, D, right? So that's why if we want to crash the leader, it will create a global impact. It is not safe to prune the reorderings. So in fact, what we're going to do is we're going to insert X at all these possible interleavings. Yes?
When you say crash, do you mean crash and reboot or just crash?
Just crash at this point.
So isn't a crash equivalent to just reordering all the messages that are subsequently delivered to after? Why do you have to model crashes at all if you're modeling message orderings?
Oh, great. So if you say it like that, then I don't need to inject crash, then I need to inject timeout. It's the same thing. Because all these red messages only happen if this thing do not see that the leader is responsive.
Right, it's just delaying the messages from the leader.
Right. Okay. Great. So what happens when we really integrate DMCK to real systems, we need to control the timeout as well. Because the timeout is usually based on physical wall clock time. So if we delay it and we cannot control where the timeout will be executed, then we lose many controls. So what happened is that's why we need to model this crash and timeout. We need to intercept those events. Now, if we inject a crash, automatically all these followers will get a network faults, and they will automatically create these red messages.
You're normally just modeling orders, but you're just assuming they happen boom, boom, boom. You're not modeling time. So crashes allow you to more concisely model time.
Yes, correct. Yeah. That's another way to put it. Yeah. All right, so this is what we call as Crash-Msg Independence. There's an independency relationship between all the outstanding messages and the crash that we want to inject. Okay? So at a high level, what SAMC looks like is that we have come up with generic reduction policies, local message independent, Crash-Msg independent, and other things here. But this is just reduction policies. If you want to test leader election, you need to map these generic patterns to leader election protocols. If you want to test atomic broadcast, you need to map this to atomic broadcast. Okay? So just at a high level, this is all the predicates that we write just to test zookeeper leader election in SAMC. In general, we just need to write a few lines of code, and this is again still a manual process. All right, so let's evaluate SAMC. So this is the bugs, the old bugs that we have reproduced, and the evaluation is how many paths do we need to exercise until we reach to the bugs. Okay, so again, if you just need 2 paths, then this is the paths. Okay, so we're going to compare SAMC with other state-of-the-art approaches, black box DPOR, random DPOR. We could talk about this offline. This is basically the MODIS from NSDI 2009 from Microsoft as well. So this is SAMC. This is how many paths or how many executions to get to the bug. This is black box DPOR. So you can see that SAMC are faster. With black box DPOR, you see some of them like 5,000 plus. This is actually, we cannot hit the bug until 2 days. And we are tight on the deadline, so I just told Tenacorn to kill the experiment. Okay. Same thing with random and random DPOR. Okay. So again, here's the speed up information. So again, overall, SAMC with semantic awareness, we can find bugs between 2 to 340x faster compared to state-of-the-art approaches, and about 50x on average among all the bugs we have reproduced. Okay? So I believe semantic awareness is powerful, and there will be definitely more rooms for improvement here. Quite, yep.
If the developer messes up one of those predicates, is it possible that you miss bugs?
Correct, exactly. Right. So that's what we are still working on right now, how to automate the process with maybe some kind of symbolic execution. Right. I mean, just annotate the message, and it will automatically find all the discard pattern, increment patterns, and maybe other commutativity patterns. Right? Exactly. Good point.
So in addition to reproducing existing ones, to try to see if there's new ones out there.
Yeah. So again, there was just tight on the deadline, so we just spent about 1 month, but we found 2 bugs in Zookeeper. One of them is considered false positive because we write the specification, there should be only 1 leader at all time, right? Turns out Zookeeper has this optimization that they allow 2 leaders at specific point in time. So I think that's again the difference between reality and the kind of book type kind of protocols, right? You need to really know what is the proper specification that you need to write. Yep. So, yeah. Yeah, Matt.
I'm just curious, what's the barrier to entry to supporting a new distributed system, like checking another system with this tool? Like, so you looked at Zookeeper, for instance, and you found some bugs. How much effort does that entail, just setting it up, integrating the tools with Zookeeper, blah, blah, blah?
Yeah, Telephone can testify to that a lot, right? So SAMC itself is 10,000 lines of code. The integration maybe takes, 500, 1,000 lines of code. Because you need to really find all the non-deterministic events, and you need to intercept them. And sometimes there are low-level implementation issues that you need to even modify the actual code to be able to be model checkable, right? Yeah. So something I think we need to discuss is how can we make distributed systems to be model checker friendly, right? To begin with. Yep.
One quick follow-up.
Yep.
Do you have any sense of how your system compares to just formal verification with something like TLA plus, or how does the effort of your system compare to writing a formal specification?
I think definitely different expertise, right? I think I still believe formal verification is more powerful because it's by proof, right? This is by hand, like you need to intercept, you need to write prune. But I think the pros and cons, again, formal verification is much more powerful, but you need to know how to write proofs, right? Not only 100 lines, but I guess sometimes thousands of lines of code, right? So you need to able to write and read proof, but this thing is just about just integrating, in Java, in C, so high-level application stuff, right? You don't need to really understand new language or whatsoever, right? Okay. Yeah. Okay, so with SAMC, we kind of ask, is model checking the only solution? Definitely not, right? So again, there's formal verification. There are other bug detection tools. So we kind of take a step back and ask, okay, can we paint a bigger picture of the problem? So we came up with this taxonomy paper. So the motivation, again, if you go to Google Scholar and you type the word local concurrency bug, it will give you, and by the way, local concurrency is the one that happens because of interleavings of multi-threads on just single machine. It will give you to this paper, okay, Shanlu YY, Learning from Mistakes, a study of concurrency bugs, right? Has been cited 500 times, top 10 most cited S+ paper, right? But if you type the word distributed concurrency bugs on Google Scholar, it will also give you this paper, right? Which is definitely wrong because, LC bug is not DC bug, right? So that's why that time we thought, okay, it would be nice to write a paper like this, and also again with Shanlu also. So hopefully this will be useful. And so far we have been cited 1 time, right? So I think we are on track to 500 citations, hopefully. Okay, all right, so what is TaxDC? This is the complete not really complete, but mostly complete, taxonomy of distributed concurrency bugs. We pick about 100 bugs in 4 varied distributed systems. The bugs reported in this 3-year window. We study deeply the description, source code, and patches. I think this took about 1 year overall. Okay. So building a taxonomy is not easy, but given the rich descriptions of the developer discussion, we could build some kind of sequence of events that lead to the bug. So for example, given the sequence of events that we have assembled, given a bug, we can see that, you need to have 4 protocol initiations to get to the bug, right? So we need to exercise the join protocol after crash. You need to exercise kind of sync snapshot. And then at one point, you need to have 2 clients running the update protocols. And then you can also see that I need to inject 2 faults and 2 reboots. And then in addition to the input, in order to get to the bug, we also see the timing violation. And again, I'll talk all about this. For example, we see update here that happens in the middle of the sync snapshot. But that's OK by itself. It needs to be combined with some fault timing that you need to inject a crash at step 6 in order to get to the bug. Okay? And there are many other informations here in this sequence of events.
So this is from bug report. That's the minimum needed to reproduce that.
Do we know whether this is minimum or not? We do not know. But this is the best description that we can reproduce to get to the bug. Okay, so again, lots of information we can come up with. So we built this taxonomy. So we can understand the triggering condition, the errors, the failure, how developers fix that, timing violation, and so on, and lots of subcategories here. Okay, so every bug will have these subcategories. So let me jump into the triggering conditions that induce the bug. I'm going to start with timing. That is the untimely events that really induce the bug. And this is interesting to help, useful to help us to design bug detection tools. Okay, so of course, again, the first kind of timing violation is messages that arrive in untimely order. We have order violation. 44% of the bugs are in this category where Y must happen after X, but Y happens before X. So again, I've shown you this before. The idea of message race in Hadoop, you have submit coming in and then kill coming in. Everything is fine. But these things happen. You kill early, and then the submit message comes late, and this gets confused. What job you want to submit? The job is gone. Right? So they get into an error. Okay? So simple message race. Talking about message race, I find that there are many different forms. This is receive race, but I also see receive send race. So for example, this black message comes early before this green, it's fine. But if the black message that carry new key arrives late, and A tells B the old key, B rejects the operations, you get an operation failure. Okay? So again, just crisscrossing. And then we have this kind of crisscrossing send race. A sends to B, let me kill the job. B sends to A. This is the end report of the job. Be confused, what do you want to kill? I just send you the last report, right? So, but if A comes a little bit early, before this message will not happen and everything is fine. So again, just different forms of message racing. And then of course, sometimes you have messages coming in and there's a background jobs running in. Yes?
That last one also looks like a receive
send race, yeah, I agree. So I just use this. Usually this is 3 nodes, but this is between the 2 nodes. But I agree with you. We could also map this to this format as well. Okay, so we have again background jobs. Again, message could arrive after that. It's fine. Message could arrive before the background jobs, or in the middle. You get to the problem. So that's order violations. Now we also have 20% atomicity violation. What does that mean? It means if you have an unexpected message comes in the middle of a supposedly atomic operation. So for example, like this is supposed to be a group of atomic operation, but then a new message comes in, then we get to a bug. But if that message comes in after or before, everything is fine. Okay? So that we categorize this as atomicity violation. Usually this message comes in from a failure, a timeout, or some operational protocol. So things that the developers usually do not expect happening in a normal runs. And then again, 21% requires fault at specific timing. So again, you could inject the crash here, everything is fine. You inject the crash here, everything is fine. But if you inject a crash maybe somewhere in the middle here, things could go wrong. Okay, so that's fault at specific timing. And again, 21%. And I think this is the major difference between LC bug and DC bug. There's no faults in LC bug. If a thread dies, usually all the process dies. But in DC bug, we need to deal with this problem. And then after you fault, you need to reboot. When you want to reboot, you reboot later. Maybe everything is fine. But again, we have cases where we see that if you reboot a little bit early, then you get to the bug. Okay? And I don't describe the bugs in detail, but I can talk more about that offline. So hopefully that, what we have come up with is that we have take these complex bugs and we try to create these simple patterns, and hopefully this can be used for like some kind of pattern bug detection tools. Yeah.
So when you look at the bug report,
yes.
you know those cases which the cause bug, right? How do you know that if you put this thing somewhere else, it's okay?
We study them. We that's why we and the students really try to understand the protocol. So we're not just looking at the description, but we really try to understand.
So you verify the other cases.
Yeah, to the best of our what we can. Right. Yep. Okay. So that's why it took a year, not just a random bug study, but really understand the problem. Okay, so let's talk about just some statistics on input to exercise the buggy code. Because why? Because this is necessary to improve testing coverage. Even in the model checking, you need to decide what is the beginning, right? And if you start with the wrong beginning, you do not get to the bug. Okay, I've been telling you that we need to inject faults, but again, how many bugs that require fault injection? Statistically speaking, 63% of the DC bug we study involve at least one fault to be injected. What kinds of fault and how many times? 12% of the bugs require some kind of timeout protocols to happen. So the timeout protocols racing with the other messages. And about 35% requires one crash and 12% requires more than one crash. We differentiate these things again depending on the description. Sometimes, as I mentioned, a crash will lead to directly a network exception. But if a timeout, usually it's coming from like network disconnect, and then timeout protocols gets regenerated. Okay? So again, we need to think about faults. Statistically speaking, how many reboots we need to inject? 20% of the bugs require a mention at least one reboot, and 7% mention more than one reboot. Okay? Now again, talking about the workload, again, let's look at this Cassandra Paxos bugs. There are these message traces, but if you ask me again, how many requests should I inject to hit the bug? Well, if this is the bug, we need to inject 3 concurrent user requests, right? So again, statistically speaking, how many protocol initiations to run as an input? 20% just happen in one protocol. One protocol can have concurrent messages. 29% 2 protocol initiations, 24% 3 protocol initiations, and 27% 4 or more protocol initiations. Yes?
When you say, so in the previous slide you said some of them require at least one crash, but they would also happen if nobody crashed, but one of the machines just had trouble sending, it was very delayed, right?
Yeah. I agree with you that in a common sense, we could always map crash with a timeout protocol. But I think just for the sake of being accurate here, if the description doesn't mention anything about timeout protocol, but it just say there is a crash, then we label it as a crash. So it's just the terminology.
The bug description rather than your analysis.
Yes, right, yeah. Because again, but we do look at several distributed systems, right? But we find that sometimes this, the network, when you get a network exception because a message cannot talk to the other node, it goes to different paths. Not in all of them. Mostly the right way to build distributed systems is to have both of these to execute the same recovery protocol. But typically, sometimes, we see different things in real implementations. Okay, so let's quickly jump to fixes. Let's ask how developers fix the bugs. This is important to help us to design some kind of runtime prevention or automatic path generation. So we thought like, okay, DC bug is quite complex, right? So it means that maybe the fix is complex. It's true that some of them, the fix are quite complex. They need to add new states or transitions, or sometimes they need to add global synchronization to other layers like, Zookeeper, okay? But what we find is that I think about 40% of them are quite simple to fix. For example, if the red message comes too early, the developers put a delay, hold that message, and replay that at the receiving side later. Okay? Or, you know what? The developers find that this red message to be benign, such that the developers will just discard that red message, and everything will be fine. Or the sender will get an exception, and the sender is added some kind of retry logic to send the message again, and everything will be fine. Or when the red message comes early, usually it is processed by a function f, but the developer realized that, well, if red message comes too early, it should be processed by another existing function g, and everything will be fine. Okay? So the point here is that turns out that 40% of the DC bugs have some kind of easy fixes that don't require new computation logic, and that has good implications to runtime prevention. Okay. All right, so these are the things that I just discussed, the green one, but again, I'd love to discuss other parts offline if you'd like to. But let me briefly mention from this study that we've come up with the challenges and opportunities in this existing approach in dealing with the problem. Okay, so let's start again with model checker. We need to permute events, but what events, right? The study shows that you need to intercept messages, you need to inject crash, reboot, timeout, local computation, and default. We have so many great papers on model checking, right? Again, Modis and Dimitar from Microsoft. I think none of us dare to really exercise all of them, right? Just going to blow our head, right? But I think in reality, we need to think about how to reorder all of them and by reducing the state space. Okay? Formal verifications, there's again great advancements in terms of verifying real actual implementation. But please do correct me if I'm wrong. We believe that they only verify the foreground protocols, which is the most important thing. But in reality, if we look at our study, most of the DC bugs happen because of interactions between some foreground and some background or operational protocols. And many of them require many protocol interactions, right? So let's try to verify more things if we can. Yes?
Go back to one slide. Yeah. Okay. I'm trying to see if you combine these two, you can cover all the.
Yes, you could cover, but it takes years to finish. That's the idea, right? So the reason why everybody could cover this.
But this fault is not covered by any the last rows.
Oh yeah, so we find that because I think distributed community just thinks about this thing. But we find that in one of the bugs, there's about, I think, 2-3 bugs where you need to inject this fault during specific operation, that this fault will lead to other messages being, happening, right? So again, yeah, we need to add this too. Yes.
Maybe you can say hardware faults in general, right? I mean, there are different kinds of things. Switches can go wrong, or disk can go wrong, or the CPU logic can go wrong. Like.
Yeah, no, but you need to intercept every event, right? If you look at the code, the one that communicates with the disk and the one that deals with the network are two different pieces of code. Right? So you need to intercept those two different pieces of events, right? And that's going to blow up the state space, right? So we cannot just say generic hardware faults. We need to be specific in terms of what hardware IOs that we're talking about. Okay. Good point.
So what do you mean by background? What is foreground versus background?
Yeah, so background means, again, sometimes you like to scale out decommissions. You try to do operational protocols like removing one node, adding one node, right? That will create new messages that will be racing with the other ones, right? I also include For example, a new leader election, you have outstanding messages, but then there's a new leader election coming in, right? That I think we include that as background protocols too, maybe.
But background protocol could be like a compaction data in the background.
Oh yeah. Okay, that too, right? So like in big table, right? There are lots of compaction messages happening in the background that compact the tables, right?
Verity and Iron can deal with some background things like extra leader elections happening.
Okay, yeah. So again, yeah, please. I'm sorry if I, yeah, but yeah. Okay. Okay. Now let's talk about bug detection. We look at LC bug, like I think hundreds of papers on some pattern-based, error-based, statistical-based. And again, hopefully, if we look at these patterns, hopefully we can use it to do some kind of bug detection. And then again, finally, prevention. We have a bunch of papers on LC bug where it's on during runtime. You figure out the bad thread interleavings, and then you fix that at runtime. I think the same way is that hopefully we can do some kind of runtime prevention as well to fix DC bugs in deployment. Okay. All right, so definitely DC bugs is important. This is some interesting of developers' comments that we find. In HBase, there isn't a week going by without some new bugs about races between distributed protocols. This is from MapReduce. So MapReduce might look simple, but you could have monster of races. Things could quite messy, and you sigh. And again, you feel like you have fixed many cases, but it seems there's like suddenly new cases. So you always miss some kind of race condition. Okay, so that's a summary here. Okay. Okay. All right, so let me move on to my second topic about non-deterministic performance bugs. I'll describe the problem of limpware, how we detect performance bugs in general, and a little bit on path-based speculative execution. So this is my first limpware anecdote. So limpware is just a cute name that I invented to specify a limping hardware. So this is in Facebook. The engineer told me that there's 1 gigabit NIC card on a machine that suddenly only transmit at 1 kilobit per second. The slow machine caused a chain reaction upstream in such a way that the 100 node cluster began to crawl at the snail space, okay? Making the systems not available for all practical purpose. So just one machine, all cluster goes down, okay? So I think, again, this anecdote is interesting because we have cases of hardware that not only work or fail stop, but also limping, right? So that's a new failure mode, and it has a cascading impact to the cluster. Now, when I hear about limpware, I go like, really? Well, I talk with many people, a production team and so on. Basically, they all just give me a big smile and they say, yes, we've seen that in production, right? And this is just a subset of the stories that, I also collected. So I think the interesting part is that, okay, limpware is real, but what is the impacts to our distributed systems? We know that our distributed systems are fault tolerant, but are they limpware tolerant per se? So we run a bunch of limpware injection experiments. We take lots of systems. We run load-intensive workload, and we inject the limpware. For example, we slow down a machine with the and slow down the network card to a slow bandwidth here. So let me give you an example. For example, we take a distributed protocol like write pipeline in HDFS, and we're going to measure the slowdowns under different scenarios. If there's no failure, then the slowdown will be 1. That's the base latency. Then we also inject a crash. So you see that the slowdown is a little bit higher here because it takes time to failure recovery. But then we're going to also inject a slow NIC. So for example, we make a 10 Mbps NIC. And if we see that the operation also slows down, for example, to almost 10x, then we know there's a problem. Okay, and then we also inject a severe bandwidth degradation, 1 Mbps, 0.1 Mbps. And if the protocol slows down, again, increase significantly, it means the protocol is not limpware tolerant. Okay? So if you see uphill bars like this, you know something is wrong. So we run lots of micro benchmark. We take these 5 systems. We test different protocols, logging, read, write, rebalancing, speculative execution, get, set. We inject the limpware, the disk, the network, and most importantly, we decide where we want to inject the limpware. Is it in the master node, data node, in the mapper, reducer, so different placement, okay? And this is what we have. Yes?
You model the limpware?
Model?
Yeah.
We just delay the network card. There's a tool in Linux kernel to delay.
But you are running, actually have a whole bunch of machines running the protocol, not the model checking anymore.
Oh, this is not model checking. This is separate, yeah, sorry, this is separate project. Yeah, so.
So can you go back one slide? So look at, is the entire workload slowed by that much, or is one slice of workload impacted by that node slowed by that much?
Just that one workload, just one benchmark.
But that benchmark runs for a while, right? It runs for like a longer period.
Depends. Sometimes 120 seconds, sometimes 9 seconds. This is the base latency. Okay. Yep. Okay. Makes sense. So for example, you create 30 64 megabyte files. Okay. So if no limping, everything runs in 180 seconds. If there's limping, maybe this runs 1,000 seconds, right? Okay. Yep.
I guess I was asking whether it's a transient thing, or if you measure long enough, you still see this slow going on for a long time. Right? Because if it's a transient thing, then.
Oh yeah. So in this case, this is not transient. We slow down in the entire of this workload.
Right. But for how long, right? You slow down the entire workload.
Oh yeah, for the entire until the experiment finishes. Yes.
Okay.
Yeah.
How slow is the hardware use?
Oh yeah. Well, I delayed it at different rates.
Yeah, but in the table, you go to the next slide. So in the table, you mentioned there's a wire, but how slow compared to the normal? Because you showed. Oh, I see.
Oh, the normal is 100 MB. 100 Mbps. 100 Mbps. Yes.
So if you, I don't understand, if you slow down the network this much, how can you even expect something to be, let's say, limpware tolerant?
Well, because like for example Hadoop, right? There's a tail tolerance, right? So if you see a progress being slow because of a network, you're gonna see that it will fail over to the other one, right? In some other cases, you have timeouts, for example, right? So you do expect that if something slows down by this severe rate, you should fail over to other systems. Because that's the premise that we built our system to be tail tolerance. But the question that is it really when we talk about limpware? Okay? Okay, so in fact, that's the answer, right? You see that this is the result, and you can just focus on the red arrows. The red arrow shows the micro benchmark that are affected by the limpware where there is no failover. The other one, sometimes it works. Sometimes there is a limpware tolerance, right? So like this, like that, right? So sometimes there is limpware tolerance, there's tail tolerance. But only in some cases, it doesn't work. So sometimes it works, sometimes it doesn't, okay? So the conclusion that this is our systems are fail-stop, but tolerant, but not really fully limpware tolerant. Okay? All right, now let me go deep. If you want to know the root causes of all these things, those are in our paper. But let me just focus this in Hadoop MapReduce, because this is where everybody scratches their heads, right? Because why Hadoop supposedly tail tolerant, but why not limpware tolerant? Why sometimes it works, why sometimes it doesn't work? Turns out there are lots of loopholes in Hadoop, okay? Let me give you some of them. Let's imagine we have two mappers here and reading from remote data nodes, okay? If this guy is slow, this guy is a straggler. If this guy is a straggler, we run another backup test. Well, turns out when we run real stuff, this backup test reads from a slow remote data node. Why? Because Hadoop and SDFS don't cooperate. They don't record some history of bad paths. Well, if you read data locally, then you're good, right? But if you read data remotely, this could happen, okay? Now let me give you another second loophole. imagine we have map and reduce, and this is the shuffling phase, and all the reducers are fetching the data from map2, and the NIC is slow. If the NIC is slow, all the reducers are slow. If all the reducers are slow, there is no straggler, right? Now, if you ask me, wait, why M2 is not a straggler? Well, M2 in this case is reading data locally. Because M2 is reading data locally, the map itself is fast. But only the shuffling phase, it affects all the reducers, and there is no speculative execution being run. Okay? Now, this is just some of them, actually. There are a little bit more. Okay? But now you can tell me that, oh, you know what, this is maybe just the unlucky job, right? You know, so be it. Well, turns out that we see cascading failures. If you have a node with a slow NIC and some other remote maps or reducers read from this, we get to those loopholes. This map and reduce task becomes limping. And if all these tasks use up all the slots in this healthy node, this node will become limping, right? If all the nodes in limp mode, then we're going to have a limping cluster, right? So that's what we have reproduced, the Facebook problem. We run this Facebook Hadoop workload on a 30-node cluster. We inject just one node with limping NIC. This is the graph. This is the elapsed time and how many jobs we have finished. In normal mode, you can see that everything about 172 jobs per hour finished. We inject the NIC at this point. We inject the slowdown at this point. So you can see that everything in the background, everything piles up, and suddenly all the cluster just produce one job per hour, just stuck in limping mode, the entire cluster. Okay? So again, that's because of the loopholes. All right, so how do we formalize the problem? Well, I find that a job is a very complex component. It could face various deployment scenarios. Let's talk about data locality. Sometimes you read from remote disk, sometimes you read from local disk. Sometimes all the tasks read from the same data node, sometimes all tasks read from different data nodes. And there's again fault type. Sometimes you slow the network, but again, where do you slow the network? Sometimes it happens on the data node, sometimes it happens on the mapper, reducer, and so on. So if you ask me what happens on this untriggered speculative execution, what I find is that some of them happens in this unanticipated scenario, only when this, and this happens. Okay? They anticipate many other scenarios, but there are corner cases like that. But that's not just untriggered speculative execution. Many bugs look like that. That's why I call this non-deterministic performance bugs. Really depends on whether you're lucky or not. Again, the blue part here happens if these blue things happen. We have seen problem with ON recovery. Okay, so this happens if you have, these four things happen. Now, ON recovery means if you have one node failing, ideally you want to just recover quickly, O1, right? But in fact, because of certain situation, it will try n times. And we also see long lock contention when all these red things happen. Okay, so again, we need to think about this problem. So some of the things that we try to do some kind of performance model checking, where we try to permute many topological failure placement scenarios. So this is still ongoing. We take a real Java code. We wrote some kind of parser or compiler that convert a Java code into a colored patronage model by abstracting only the system level construct like the queues, tasks, resources, and locks. And ideally, we want to permute all the placement scenarios in CPN. But I think the most important thing is that we abstract performance faults. We just need to get the final result, whether the task will be limping or not. We do not need to have precise latency or bandwidth prediction, because we're not trying to accurately predict the performance model, but just try to get a sense whether things will be in limping mode or not.
Hi,
Okay, I raise my
Yeah.
hand first.
That's fine.
So your previous couple slides got the fonts really small. So here, do you assume there are other faults in addition to the limping nick? Or
Oh yeah. Sorry about that. Yeah. So I think when I get to this slide, I take the problem in a little. I see the problem a little bit higher level ups, right? So where we study more performance bugs. So now the fault type, you're right. It could be, I've seen like slow node or nick. I could see this error out of space. I could see not only nick that is failing, but I also see rack switch that is failing. And that gives me different scenarios. Yeah.
I think your work is very interesting. And do you think this is I'm not sure. Do you think this is a problem at two different levels? And if you have a better monitoring at the network level without having the distributed system protocol worry about this? Because 0-1 is easy to handle. Limping nick is like a network wire. I
think you're completely right. I've been also thinking about the problem, right? Where should we solve this problem, right? Is it a separate But I think the problem is that when you talk about a network slowdown, I know that I'm not a networking person, but network is a beast, right? If network looks slow from a perspective of an application, that's literally that the real network is slow, right? So although I say limpware, right? But it is also possible that you get a huge network background jobs that from one perspective of the application, the network looks slow. It looks like a limpware, right? But actually the network hardware itself is fine, right? So, again, the thing here is that I also want to say is that the fact that we already built our systems with tail tolerant in mind, right? So it's already there in our systems, but it just doesn't. If I can take another lesson from here, if we think about just tail tolerance, it's just within the Hadoop MapReduce protocol. But if you see these problems, they're like submit jobs, right? Cleaning up files. There are so many other protocols that are still not tail tolerant, and that could affect the main jobs itself. That's my high level takeaway points, right? So yeah, great. Yes.
So just on the inside, so do you think you need to integrate tail or the limping fault tolerance into the models, or do you think it should still be separate like the way we do it today, like fail stop different part and detecting the limping as a different part of the problem? Because transparency is something which...
Yeah, I think it's different part. I don't think we can do tail tolerance as part of like fail stop tolerant. But again, what I'm saying here is that, I didn't invent tail tolerant, but definitely that's where everybody is going with tail tolerant, right? What I'm saying here, let's look at the broader picture where tail tolerant is not just about the job itself, but there are so many other protocols that running in that systems that require to see the problem of tail tolerant. And it's just coincidence that I find this problem by starting looking at the limpware problem, right? So I start looking at limpware, but I see the problem going up, and you get this bigger picture that everybody needs tail tolerant. Okay? Yeah.
So what I was going to say is, I think we were 2 slides ahead. One thing I was expecting to see here, it seems like something. By the way, I like this work on tail tolerance. I think it's very important and formal methods have nothing to say about it. It seems like one requirement for something to be a limping fault is that there is actually something you could do about it. So if the NIC is if the disk is busted on the one machine that has the data that you need, then it's not a bug in the software that is going to go slower because that.
Right, great point, right? The assumption here is that when I talk about limpware tolerance, is that there is another healthy node where we could fail over to, right? I agree with you that if this is a single master, and the problem is there.
So where does that come into this? Into your model for whether something is limpware tolerant or not?
I see. It comes in where the fault we inject, right? For example,
I see.
if the system is one master, we're not going to inject a slowdown at the master, right? Yeah. Okay. Yeah. Good point. All right. So
Sorry. Another question. So there is another class of faults. For example, when a NIC is dropping, say 5% of the traffic or certain IPs because of some bug on the NIC itself, right?
Right.
How could you like model those kind of things because in a way that's kind of slowing down or impacting certain services or applications, not all of the cluster, right?
Yeah, we do see this problem where there are some packet drops and it affects the performance of the system somehow. But I think that's a different model, and I'm not trying to be greedy and solve all the problems here. But that's a good point. And in fact, we do see that problem. Okay. All right. So and on a separate things, this is also nearly in submission. How do we fix speculative execution? I think the problem is not in the algorithm, but I think the problem is that if we look at the definition of a straggler, it's like a T that is slower than the rest. But what is a T? A T is just a progress score of that task. But from this experience, we find that a T, task T, is a path, right? For example, if you have a map, sometimes you read from locally, but sometimes you read from the remote data node. So that's a path. You need to remember the progress of that path. And the shuffle is between a bunch of map nodes and reduce nodes. And then there's an output path as well, right? So PBSE basically says that it's all about the progress of the paths, not just the individual tasks. And we still can retain the existing algorithms. And hopefully with PBSE, we do not have a single point of path failures because we try to diversify the paths. And I have some backup slides on this, but let me just move on quickly. So just scalability bugs, this is in submission, so I just have 2 slides on this just quickly. So I start seeing these bugs where this is latent bugs that are scale dependent. So meaning that if you imagine you have a bug symptom on the y-axis, let's say for example time to rebalance or time to bootstrap the cluster, you do not see the symptom unless at one point you start having 100, 200 nodes and it goes up, okay? So this is what I call as scalability bugs. Now, would it be nice if we could, scale check our distributed systems prior to deployment? And then, or we could debug all these large scale bugs, but do just that on one machine, okay? So this is the vision that we try to get with this idea of SCK, scale check. Now, in terms of the state of the art, I believe there's only one very close related work on this whole problem. This is Exalt from the University of Texas, Austin. What they focus is on the data path bugs. So the problem is how to collocate space-intensive data nodes on just one machine. So they basically create a compression where they make a data illusion, so that the data does not exist, because they say that how data is processed is not affected by the content of the data, but only by its size. So they just try to memorize the size. With this, they can collocate up to 100 data nodes per machine. I believe they run HDFS with 10,000 nodes at the end with a bunch of machines. Now, SCK is not really competing with Exalt because we focus on control path bugs. For example, when you run Bootstrap on 200 machines, when you run rebalance, or when you have 100 machines, you scale out again 100 machines. Is everything okay? Turns out in these control path bugs is that everything is quite CPU intensive, not space intensive. So the solution, we kind of have this idea of processing illusions, memorizations, and so on. Because similarly with this intuition, our intuition is that how compute matters is not because of really the intermediate computation, but rather by its execution time and output. Okay? So at the end, we can collocate up to 500 nodes. We could reproduce 6 scalability bugs in Cassandra and React and one other systems. So we believe these 2 things are kind of orthogonal, but again, that's at a high level the problem of scalability bugs. All right, so I read slide number 90, so I guess I should conclude. So again, these are all the interesting bugs that I'm trying to work on. If I may conclude in just one sentence, I believe the complexity of cloud-scale hardware and software ecosystem has outpaced existing testing, debugging, and verification tools. This is a negative note, but I guess the positive note is that for us researchers, there are new classes of bugs to hunt. Okay? All right, so that's it. I'll take more questions now. Yeah.
Just going back to the limping bug that you were talking about.
Okay.
So say there are networks are very diverse, right? So one of the switch is has this limping fault, and it's in one of the paths, right? And there are several paths that exist to talk between, say, compute and that is CPU on the disk, right? So it won't show up in these kind of verification where it's a partial slowdown, it's not a complete slowdown, and some of the services will get impacted while others will run just fine. So how do you propose to detect those kind of
Sorry,
faults?
could you rephrase the
Okay, so say like there is a path A, B, C, and
yes.
B has A connects to B, B connects to C, and B has the limping fault.
Yes.
And there is another say compute which is D, which is connected to E and B directly, right?
Okay. Yep.
So there are now two paths between for D to reach C, that is B and E.
Okay. Yep.
But B has a fault.
Yeah.
So it won't show up exactly. So for A it will show up as a limping fault, but for D it won't show up because there exists another path to reach C.
Yeah. Right.
So how do you do you take that into the account when you do the
Right.
analysis?
So I think my way to address that question is that if we look at this problem, this is like network routing problem, right? I mean, there's lots of slow routers all over the place, right? But I think if I look at speculative executions per se, I'm not talking about really long path, right? I mean, I'm talking about more like lots of parallel tasks with small paths, right? And all we need to just make sure that there is no single point of failure. There's no like multiple paths where that goes to the same slow hardware, because if you do that, then the speculative execution will not run, because speculative execution depends on straggler. One of them must be slow, right? So we try to diversify the path. In your case, if that is the case, then I think the speculative execution will run fine, because it will see one thing goes fast and the other one goes slow, right? So that's good. What we need is to diversify.
But I'm just guessing that it's a very Hadoop specific model that you're talking about.
Yeah. Right. I mean, I try to solve one problem at a time, but I think now I think going back outside Hadoop, I think it's all about permuting all the possible scenarios, right? And I think again, the reason why we came up with all these problems because we do a placement, fine-grained placement injection, right, at different nodes, and we uncover this problem.
Do you have a vision for how all these tools will eventually get in a form where ordinary developers can run many of them at once on their code, maybe even before it's finished?
I don't have the visions, but I've been trying to integrate this to real systems, right? So maybe close to real adoption. I think to me, I think the high-level lesson is more like educating our production teams and engineers about these tools, right? Because they need to build the systems to be model checker friendly from the beginning, right? I've talked about scale check. I don't talk about the details, but I need to change a lot in the target systems to make it really scale checkable, right? So I think it depends, like if you really want to build distributed systems and you want to make it really reliable, then there must be a path in terms of how we should re-architect our systems to be model checkable, scale checkable, performance checkable, and so on. So that's my thing.
In your taxonomy of bugs, you also taxonomized the fixes, and I was wondering if you found anything about which fixes didn't work. You said some fixes are complex and some are simple.
Right.
I'm curious, are the simple bugs more likely to not work or more likely to work?
That's a great question. Unfortunately, I think we don't analyze that further, but we do see fixes. I think this is typical. We do fixes that fix that protocol, but it causes other problems in other protocols, right? Thanakorn, you want to add something to that?
Sometimes we see some fix that introduce new bug. Yeah, but in our study, we don't study like in one issue, one report. We don't see that. We don't study that. We have multiple fix in one report, and we study all that fix. At the end, we study just the work, the fix that work. But the work fix may introduce new bugs in other report. So we study just two fix like this, not the detail.
Anyway, that's just something I'd be curious about, because it seems like simple bugs are perhaps less likely to induce other bugs, but maybe not.
Yeah. Right. In fact, we were talking a little bit about this, right? I think like the idea of model check, hopefully scale check should be deeply integrated, because at least if we look even this more like popular modern cloud systems, and we see that this practice that people say, oh, there's a bug, and they're just going to focus on that bug and on that protocol, and they fix that, they check, yes, one bug has been solved, right? But the implication to the whole ecosystems, they don't see it in that particular thing. Yeah.
I really like your research. It's
Okay.
really awesome. So my question is, so the model checking is similar to, the system model checking is similar to random model checking. It's explosional, right? The state space. Even if by the heuristics, it's still explosional, right?
Yes.
So I was wondering, as you mentioned, so can we do something that have the programmers, when they develop these tools, they can have some guarantees with the presence of these hardware failures or these interweavings. So I was wondering if you can do something. Is there any work on that level, like program boundary level?
You apply verification to the link
what we described this approach that the program has this system built, and then you apply this to this.
Right.
Can we do it on the fly with the developer?
I guess the answer is always yes. I believe like with software, you could always do anything with software, right? I believe the answer is yes, but I'm sorry, I'm not like a formal verification guy, so I'm not really know or could see how we should do that. But I believe yes, there's the answer to that. Yeah.
Yes. Inspiring is not the purpose of the talk, right? Let's thank Professor.
Okay.
And come to tomorrow's talk as well, right? Tomorrow morning, 11 o'clock.